6 years ago, I've made this Arduino-based laser projector using stepper motors. After the project was published by Hackaday and shared on Arduino's social media, I've started receiving a lot of feedback from people interested in knowing more. The video on YouTube also got a lot of views.
Wow!
Well, at least relative to the amount of my subscribers. However, since then my approach towards electronic projects changed a bit, and instead of using modules like Arduino, I'm trying to design my own PCBs and use technologies as CAD and 3D printing. Therefore, looking back to how this was done, I have some improvements in my mind that I would like to incorporate, and that's exactly the reason why I decided to make this upgraded version, which I will share with you in this video. So let's get started! First, let's discuss some basic theory. Lasers, compared to other sources of light, such as an LED in a standard flashlight, have a unique property of being coherent. This means that the radiated light waves not only have the same frequency, but also travels in phase with each other. Laser light is also highly directional. The beam has a very low divergence, staying narrow over long distances, ultimately producing a small dot on the incident surface. Moving this dot fast enough can trigger our brain to perceive it as a pattern instead of a single moving dot. This is caused by an optical illusion called persistence of vision, which is the same phenomenon allowing you to watch this video while I'm showing you 60 individual still images every second. Since moving the whole laser body is limiting due to its mass, we can use mirror to deflect the beam instead. By using two perpendicular mirrors, each having a single pivot point, the beam can be deflected in X and Y axis. This design allows to easily drive them with some kind of actuator. The only limiting factor is how fast and accurate the mirrors can be moved. In traditional laser projectors, these mirrors are usually driven by a component called galvanometer, or simply galvo. When current flows through a wire, a magnetic field is produced around it whose strength is proportional to the amount of the current. Direction of magnetic field lines can be determined by the right-hand rule. If we point our thumb in the direction of the current, then the fingers are indicating the field line direction. Making the wire longer and forming a coil does not change the direction of the field lines, so they superpose and eventually increase the overall magnetic flux density, making the effect stronger. Placing this coil in the field of permanent magnets causes them to interact with each other. The original galvanometers used this principle to measure current. The spindle, consisting of the coil attached to a long thin pointer, was placed between two permanent magnets, used as an indicator on a scale. It was held in the center by a torsion spring. The higher the current flowing through the coil, the stronger the electromagnetic field, and the more force is generated against the resisting torsion spring. That way, the resulting position is proportional to the amount of the current flowing through the coil. This design was further improved by replacing the pointer with a tiny mirror, so it deflects light to the scale instead. This massless pointer greatly reduced the mechanical limitations of the long one. Nowadays, galvanometers are mostly used not in current measuring applications, but quite the opposite, using a known current to precisely position the mirrors. The design was optimized even further by using a tiny circular rod magnet placed between two coils. Compared to the previous design, the moving part is now the magnet, which removes the need of any wires being attached to it. Another improvement is the removal of a torsion spring that negatively influences high-speed operation at some frequencies. This is done by implementing a closed-loop feedback control, where the actual position of the shaft is continuously monitored, usually by a capacitive or optical encoder, and thus the driver can error correct and adjust the coil current to keep the mirror precisely in a given location. This principle works great, and in high-end applications can achieve speeds even greater than 60 kilopoints per second, which means that every second the mirror can be moved to 60,000 different locations. In fact, the very same principle is nowadays used in many industries and products such as modern SLA and SLS printers, laser cutters and engravers, ophthalmological systems, and more. The only downside of galvos is their higher cost, and that's the reason why I'm sticking with stepper motors for this upgraded version. Initially, I tried to use small NEMA 8 motors mounted on a 3mm laser cut acrylic. However, this option did not perform well at high speeds, and the motors were not quite cheap either. Later, I discovered these 25mm stepper motors from AliExpress. They have an internal metal gear with 1:12 gearing ratio, output D shaft, and cost less than $2 each. The only downside is that I couldn't really find their datasheet based on the model number, so I had to use the specification from the seller. Stepper motors don't have an encoder to determine their current position, but that is not a problem since they rotate in discrete steps. That way we can just keep track of the position digitally, assuming that they don't skip any steps. Doing it this way, however, requires homing to be performed on system start, where the microcontroller drives the motor to a known reference location and sets the position tracking variables accordingly. In this case, the homing sequence makes sure that the microcontroller knows where the origin of the projection plane should be. In the original version, I used the photodiode to detect the passing laser beam, which is very far from an optimal way of doing it. It requires the laser to be on, and in the worst case can take quite some time, since there is only one position that both mirrors needs to align to. This time I want to be able to home both mirrors individually in parallel and without the laser. I need a component that mounts the mirror to the motor's output shaft. If I make a thin plastic protrusion on the side of it, it will be always in the same position and angle relative to the mirror, so I can use a sensor to detect it and use it as a reference. For this, I've designed two tiny PCBs to be mounted parallel with X and Y steppers containing QRE1113, which is a tiny infrared reflective sensor commonly used for line follower robotic projects. It consists of an infrared LED positioned right next to a phototransistor, both facing upwards. This way, the amount of reflected light is proportional to the collector emitter current that we can measure. These boards connect to the main PCB, which contains the ESP32 module, two buttons for controlling the modes, one of which is connected to IO0, allowing the ESP32 to be put into bootloader mode for flashing the firmware, switching step-down regulator for battery operation, connectors for battery, homing sensors, laser and programmer, two MOSFETs, one for PWM laser control and another one for power gating the homing sensors while not in use, and two stepper motor drivers based on ST-SPIN220, which I think is a very nice alternative to the commonly used DRV8825 and 8880 drivers. Compared to them, it can push a little less current, but on the other hand it operates down to 1.8 volts, which is perfect for battery operated applications. So, having the design ready, it's time to get the PCB manufactured.
A few moments later.
Well, that was fast. Let's do the fun part. I'm still using the metal hard drive disc platter as a mirror, but this time cut into much smaller size. There are 3 mirrors in total, one for guiding the laser beam and 2 for XY deflection. Instead of using a laser cut acrylic, I've decided to model the base as a single piece and 3D print it. After all, it's simply a more accessible manufacturing technology for makers. The firmware is written to allow Wi-Fi connectivity both in AP and station mode. It spawns a web server where the user can control the laser, select animations, speed, and change settings. All the commands are defined in a simple protocol sent over WebSocket. These features, however, act only as a proof of concept, and the code can be expanded to accept commands through other interfaces like serial and Bluetooth, and use protocols such as MQTT, real-time UDP, DMX over Ethernet protocols such as RNet and SACN, or even ILDA. The module has enough computing power to support it. I'm not going into details with the rest of the code responsible for driving the steppers, homing, and animation functionality, but I'm releasing all the design files and source code on my website, so feel free to check it and get inspired if you decide to build something similar. If you like this project, don't forget to hit the like button and consider subscribing to this channel. It means a lot to me, and I have more projects in making. Actually, I'm already thinking about the next version of this project, where I'm completely getting rid of the stepper motors, so stay tuned. Thanks for watching and see you next time.